All right, so we should be on this page here. At the top, it should say graphing translations. So far, we've gone over how to do reflections and rotations. We're going to now talk about that third type of isometric transformations, which is the translation. And remember, last unit we talked about a translation being something that just slides something around. It pushes it left, right, up, down. It's not flipping it over like a reflection does. It's not turning it like a rotation does. This is a little bit different. Inside of our translations today, we're going to see things called vectors. And so we're going to need to talk about how do you work with the vector and read and understand what the vector is telling you. So just like the other things that we've talked about, we've had notation that they use. Remember, we use like little r for reflections, capital R for rotations. So for translations, you're going to see a capital T. And right next to that, instead of parentheses, they're going to have these vector notations. So it looks a little bit different than like a coordinate because it doesn't use parentheses. It uses almost what looks like less than and greater than signs. They're kind of like almost the arrowhead, but just without the line attached to it. And then in here is going to be numbers like 2, -5, for example. And then after that, in parentheses, is going to be a letter or it could be a shape. So remember, the capital T stands for translation. This 2, -5 piece that I put in those kind of pointed brackets, that's your vector. And the A that's at the end, this is what's being translated. So it still has some of those same elements that our other notation had, but let's talk about that vector a little bit more. So vectors are describing how it's being moved. Vectors are kind of like, I almost think of it as like, it's like wind. If you ever like have watched like the weather in the morning, and sometimes if they're talking about what it's going to be like during the day, if they especially are talking about like wind, or even maybe after like a storm, or if we had like really windy days over the weekend, they'll show on the weather map vectors. Like they'll show these arrows that kind of describe this is the direction that the wind is coming. It's blowing up from the south, or it's coming down from the north, or it's going at a different direction, and they'll show that using vectors because they'll have like these little arrows that kind of show the direction that the wind was blowing. And that's kind of what's happening when we talk about them in geometry. We are talking about something like a force of some sort that's pushing our shapes around on the graph. And sometimes they'll use the vector notation. Sometimes they'll use like an arrow on your graph to describe where it's going. But when you look at your vector, like I said, it kind of looks like a coordinate because you have two numbers on the inside, like an X and a Y, that are separated, with a comma. And we've seen that before with coordinates, but instead of it having those parentheses, it's got those pointed brackets. So let's talk a little bit more about these elements. So the X on a vector is going to be talking about the horizontal movement. Think about your graph. Your x-axis is that horizontal axis that we have. And so when you're moving along that, you're going left or you're going right. If you're going to have a positive number here, so if the x value is positive, that means that it's going to push your shape to the right. If you have a negative number in for your x value, that means you're going to go to the left. And if you think about your number line on the x-axis, that should make sense. If 0 is in the middle and you go to the left, you're going towards negative numbers. If you're going to the right, you're going towards positive numbers. The Y is going to represent your vertical movement. So if it's a positive number for your Y, what direction do you think that means it's going to go? Good, up. And so negative would mean down. So when you look at that, you have to look at the numbers and you have to understand if it's positive versus negative, that tells you what direction your shape's going to go. Now, when we get these started, we're going to go back to that dot paper that we've seen before. Could you use patty paper here? Yes. However, I would almost recommend that you don't use patty paper for translations because it's almost more confusing to trace the shape and try to move your patty paper the directions versus just counting the dots that you see on your dot paper. So I'm not going to use patty paper today, but just know that you could if you wanted to. But the first thing that I need to do is when I look at my vector, I need to understand what directions it's going to go. So if we look at this first triangle here, your vector is right here. It says 2, -3. So what does the 2 mean? What direction are we going?
Right.
Right. So we're going to move everything right 2, and then the -3 means down 3. Good. So going here to my graph, onto my dot paper, I'm going to start with K. I'm going to go 2 to the right. So I just count 1, 2, and then you go down 1, 2, 3. And this is where your new K should go. And remember, we call those primes. So K prime's going to go right there. And you don't have to draw all those things in. I was just showing you how to count because sometimes kids will start counting on the wrong dot. Okay, we're going to do the same thing with H and with J. So I'm going to go 2 to the right, down 3. Then once you've got your points on there, you're going to connect. Okay, so thinking about that vector again, remember I kind of gave examples of when you would see vectors used. Sometimes we're going to have arrows on your pictures to describe the movement. So sometimes what you'll see, and you'll even see this on your homework, that's why I'm talking about it today, is they'll have like an arrow drawn from J down to J prime like that, showing the vector movement. So you'll see that on your homework today. They'll have these arrows kind of drawn in, and it just means that they're trying to describe the movement that the vector had. Like what direction did your shape go? And so your shape should move along that arrow. It shouldn't be fighting against it or overlapping with the arrow. And really, if you think I should be able to draw those arrows that connect all of my points. And so everything goes in the same direction. We talked about that last unit when we talked about like, do some points move farther than others? Not for translations. Everything has to move the same amount. Okay? I want you guys to take a couple minutes and try to do these two on your own. Okay, let's talk about these. For that first one, triangle EEF, what direction did you guys move?
Right.
Right? Did you go up or down at all? No, because the Y is a 0. So you just needed to move all these points 6 to the right. Okay, and then how about for the second one? What directions did you go? Good. Left 3, down 1. Both of those numbers were negative this time. That's why we're going in these directions here. And that last one, they will overlap just a little bit, and that's okay. Just like we've seen shapes overlap sometimes with reflections and with rotations, it's going to happen at points with the translations. If the vector isn't like a big enough vector to really move them far apart from each other, they might overlap a little. All right, any questions on how to do that on those dot paper problems? Now, you could use this same process if you were on the coordinate plane. You can see on your page here, we don't really have anything that's on the graph, on the X and Y axis, but it would work the same way. You could have a shape put on the graph, and then you could be moving it left, right, up, and down. It's going to work very much like what we just did there with the dot paper. What they're going to kind of switch us to down here is we're going to be working with that notation. We're going to kind of go back and forth between the coordinate rule notation that we've seen before with our now new vector notation, and then also sometimes they're going to give you the original point, sometimes they're going to give you the new point. You have to be able to read through the notation and understand, what are they giving me, what am I looking for? Just like when we did that with functions, understanding, do we plug it in, or are we given the output, like being able to set them up differently like that. The first ones want us to take our movement from our image to our pre-image, and they want us to do two things. They want us to write the coordinate rule, and then they want us to just change it to a vector, because we should be able to go back and forth now between coordinate rules and vector notation. So to do that, you first need to figure out what happened with your coordinates, like what changed with the X and what changed with the Y. So if you start on this first one, my X starts out as a -4 and it goes to a -1. So I'm just drawing an arrow to connect those numbers together. What did you add or subtract to -4 to get to -1, Jackson? 3. You took, did you minus 3 or add 3? Added 3. So if I take -4 plus 3, that should equal -1. Okay? But let's say this is just one point from like a triangle that we have on the graph. If I then wanted to do the same movement for all of the other shapes, I would need to be able to write out a coordinate rule for that. So to do that, I took my X value, in this case is a -4, and I added 3 to it. So that's my coordinate rule. And we have seen coordinate rules before. This is what you guys were working with last unit. Now today I've talked to you guys about vectors. So if you come over here to write your vector notation, all you have to do is take the number that you're impacting the letter with. So in this case, it's +3 because we're adding it. So I'm just going to write 3. And that's the only difference between coordinate rule notation and vector notation. Okay, now let's do the Y. The Y starts at 1 and it goes to 3. What did we do there? Keegan? Added 2. We took 1 plus 2 to get to 3. So over here I would write that as Y plus 2. And then what number would I take for my vector? Just a 2. If they gave you the vector 3, 2, you should be able to write it as a coordinate rule. You should be able to write X plus the X from your vector, Y plus the Y from your vector, or minus if the numbers turn to negatives. That sign is really just going to kind of pop in the middle. You guys try the second one. Write out the coordinate notation and the vector notation. Okay, who's got an answer they want to share with me? Keegan?
X -4 and Y -1.
Everyone agree so far? X -4, Y -1. How'd you then write that as a vector?
-4, -1.
Good. Okay. This next chunk of problems here, guys, we're kind of going back and forth between all the things that we've learned, like coordinate rules, vectors. Are you looking for the input versus the output? So make sure you read these carefully so you know what to do. So for part A, this is kind of going back to what we did in the last unit. They're giving you guys that coordinate rule. They're telling you what you're doing with the X and the Y. They're giving you the coordinate to apply it to. How are we going to handle like A and B? Because they're both very similar. Greer, what are you going to do? Okay. Yeah. You're just plugging it in. So if you guys do the same thing with letter B, what do you get for an answer? Keegan?
3 and 4.
Good. 3 and 4. Because you're going to take 4 minus 1 and 3 plus 1. You're just plugging those points in. They're giving you the original point. That's your input point, so that's why we're plugging it into our rule to get our answer here. What's different about letter C? What'd they switch on us for letter C?
It gave us the output, but not the input.
Okay, so it's not giving you the input, it's giving you the output. Do you guys remember what we would do with these ones in the last unit to figure out what the input was? Maisie? Yeah, so take the rule and set it equal to your coordinate that you ended with, and then you worked backwards to figure out what the x was. Now for this first one, do you guys see how it just says x? It doesn't say x plus or minus anything. So it's just, if we come over here, it's going to be x equals 8. So did anything happen to their x coordinate? No. That would be the same thing like in a vector. What number would be there if nothing goes on? 0. Good, because it doesn't go left or right at all. It just stays where it is. Okay, now for the y, my rule says y minus 4, and my output here is negative 5. So y minus 4 equals negative 5. What would you get if you solve that? Negative 1. Good. Okay, now switching down to D, E, and F, they're not giving you the coordinate rule anymore. They're giving it to you in the vector notation. But we handle these the same way. The vector notation, you're still going to add or subtract your numbers. Just look at that vector to figure out whether you add or subtract. So for this first one, your vector is negative 1 and negative 2. So both of these numbers that you start with, you're going to have to subtract. You're going to take 9 minus 1 here. And you're going to take negative 5 minus negative 2. Or sorry, minus 2. Not a double negative there. Okay, so what do you get for answers? Good, 8 and negative 7. Let's jump down to F, because F is the same as that. If you plug in your point 0 and negative 7, if you work with the vector there, what are you going to get? Negative what? 4, negative 10? Yeah, sorry, I skipped the middle one because the last one's very much like letter D. Yeah, so we took 0 plus 4 and then negative 7 minus 3, and you got 4, negative 10. Okay, now let's go back up to that one in the middle. Okay, and what did you say you got there, JD? Okay, can you just explain how you got there?
Yeah, so 5 minus 6 is negative 1, so then you would get that.
Okay.
And then you do 0 minus 7 is negative 7.
Okay.
What negative 1 is.
Yeah. So again, you could set up an equation here, guys. You don't know what the x is originally, but you know you took x plus 5 to get to negative 1. And that's why he was saying he subtracted the 5 from the negative 1. Because he's kind of already mentally setting it up, and then he's subtracting. Then we do the same thing with the y. It'd be y plus 0 equals negative 7, and that's where that negative 7 comes from. Okay, last problem we have here says that point A is translated by the coordinate rule x minus 3, y plus 5, followed by another translation of x minus 7, y minus 1. Write a single translation using vector notation that would result in the same movement. What are we going to need to do here to get one single vector? Any ideas, group?
You take two things being subtracted from x and then you would add them together in the same thing with y.
Okay, so I have x minus 3. So you said take the negative 3 and the negative 7 and basically put them together. Yeah, and that becomes what? That's negative 10. And then my y's are a positive 5 and a negative 1. So you could think 5 plus negative 1 or 5 minus 1 would be 4. Okay, so my combined vectors would be a negative 10 and a 4. How do I write that though in vector form? What does that look like, vector form?
Like the two, whatever, like the, I don't know what to call it.
Those little pointed brackets, right?
Yeah.
So I need a capital T for translation. I need my brackets here. And what goes on the inside?
-10, comma 4.
Good.
And then wait,
I think that's it for vector notation. Oh yeah, but it could be whatever point, I guess, yeah, after that. A. Okay. What if they had said to write it as a coordinate rule? What would that look like instead? Keegan?
x minus 10 and y plus 4.
Yeah, it would look like this. Yeah. This is what they asked for, but just know you could go back and forth. They might ask you to kind of do that. So you should be able to, like, pretty fluidly be able to go between coordinate rules and vectors now. Okay, any questions on translations?
Okay.
Okay.